What if the key to Allied air superiority in World War II wasn't tactics, training, or numbers, but 12 cylinders and a secret that Germany's finest engineers spent years trying to steal and never could? In the summer of 1943, as P-51 Mustangs began escorting American heavy bombers deep into the Reich, the Luftwaffe's high command faced a sobering realization that was not about pilot courage or fuel reserves or even strategic doctrine. It was about an engine, specifically the Rolls-Royce Merlin, a power plant so precisely engineered, so demanding in its tolerances, and so deeply embedded in an industrial ecosystem that no amount of German ingenuity, ambition, or urgency could replicate it at the scale the war demanded. And that singular failure, more than any single air battle or strategic bombing raid, quietly sealed the fate of German air power over Europe. The story begins not in Germany, but in Derby, England, where Rolls-Royce had spent the better part of a decade transforming a promising but troubled piston engine design into something extraordinary. The Merlin's roots lay in the R engine that powered Britain's Supermarine S-6B to victory in the Schneider Trophy races of 1931, a brutish, racing-optimized power plant that burned a fuel mixture closer to aviation cocktails than anything sensible, producing over 2,300 horsepower for barely long enough to win a race before its components began destroying themselves from the inside out. What Henry Royce and his team of engineers extracted from that experience was not a working production engine, but something more valuable, a set of principles, a metallurgical intuition, and a manufacturing culture that would eventually produce the Merlin, a V12 engine displacing 27 liters that entered service in the Hurricane and Spitfire in 1936 and 1937, and would go on to power more Allied aircraft types than any other engine of the war. The Merlin was not a simply piece of machinery by any measure. Its cylinder block was cast from a special aluminum alloy developed through years of collaboration between Rolls-Royce and British metallurgical firms. Its supercharger, the mechanically driven compressor that forced air into the cylinders at altitudes where the atmosphere thinned to near uselessness, was a masterwork of close tolerance engineering, with impeller vanes machined to specifications measured in thousandths of an inch. Its two-piece cylinder head design, which had caused the engine persistent early reliability problems, was eventually perfected through a combination of improved casting techniques and a revised coolant system using a pressurized ethylene glycol mixture that allowed operating at temperatures high enough to extract more power without boiling the coolant away. Every one of these refinements had come through painful, expensive iteration, through engines that failed on test stands and blew cylinder heads over the English countryside and seized their bearings on combat missions at the worst possible moments. And every failure had taught Rolls-Royce engineers something they wrote into the next version. By 1940, the Merlin III, powering Spitfires and Hurricanes during the Battle of Britain, was already a dramatically improved machine compared to the Merlin Y that had entered service just 4 years earlier, and it was still evolving. The Germans were well aware of the Merlin before the war began. Intelligence reports from the mid-1930s onward tracked British aero engine development with reasonable accuracy, and German engineers had access to technical literature and even on occasion to demonstration aircraft at international air shows. What they observed was impressive but not, they believed, insurmountable. Germany had its own world-class aero engine industry centered on Daimler-Benz and Junkers Motorenwerke, both of which were producing competitive liquid-cooled V12 engines in the DB 600 series and the Jumo 210 and 211 families, respectively. The Daimler-Benz DB 601 that powered the Bf-109E during the Battle of Britain, was, in many respects, a sophisticated piece of engineering featuring direct fuel injection rather than a carburetor, which gave German pilots the ability to push their aircraft into negative G dives without their engines cutting out, a genuine tactical advantage that British pilots in carbureted Merlins could not initially match. But the German engines and the Merlin were evolving along parallel tracks toward a confrontation that would not become decisive until 1944, and the factors that would determine that outcome were already being set in motion years before the war's critical air battles began. The specific moment that forced German engineers to take the Merlin seriously as a problem to be solved, rather than simply a competitor to be beaten through independent development, came in early 1944, when the P-51 Mustang, equipped with the Packard-built Merlin V1650, began appearing over Germany. The P-51 had existed in an earlier form, powered by the Allison V1710, an American engine that was technically competent but lacked an effective two-stage supercharger, limiting the aircraft's high-altitude performance precisely where long-range escort work demanded it most. The transformation of the Mustang into a war-winning aircraft had come from a seemingly simple substitution, replacing the Allison with the Merlin, but the engineering involved in that substitution and the industrial story behind it was anything but simple. The Merlin had crossed the Atlantic because Rolls-Royce had licensed its production to the Packard Motor Car Company of Detroit, beginning in 1940 in a transaction that deserves to be recognized as one of the most consequential industrial decisions of the entire war. Packard was not an obvious choice for such a demanding assignment. The company made luxury automobiles. Packards were among the most prestigious American cars of the era, and its manufacturing culture was oriented toward quality and craftsmanship rather than volume production. But Packard had the engineering talent, the machine tool inventory, and crucially, the corporate willingness to remake its entire manufacturing operation around a foreign engine design, and it had done exactly that. What Packard's engineers discovered when they received the Merlin drawings and sample engines from Derby was something that simultaneously impressed and alarmed them. The engine was exquisitely designed, its components engineered to extremely tight tolerances, and its assembly sequence demanding a level of attention and skill that went far beyond what American automotive mass production normally required. The Merlin was not a simple bolt-together machine. Its connecting rods were balanced to within fractions of a gram. Its supercharger rotor clearances were measured in tenths of a millimeter. Its valve timing was set to standards that required specialized gauging equipment that Packard had to develop from scratch because the British equivalents were calibrated in different units and built to British standards that did not transfer directly to American machine tools. Packard spent the better part of a year redesigning the Merlin for American manufacture, not changing its fundamental architecture, but systematically converting every dimension from British imperial to American standard measurements, substituting American specification alloys for British ones where direct equivalents existed and developing new specifications where they did not, redesigning certain fasteners and fittings to use American thread standards, and building an entirely new inspection and quality control system around the engine's demanding tolerances. The result, the Packard Merlin or V1650, was functionally identical to its British counterpart in performance, but manufactured to American drawings with American tools by American workers, and it could be built in quantities that Rolls-Royce's Derby facility, no matter how efficiently managed, could never approach. At peak production in 1944, Packard was building Merlin engines at a rate that exceeded the entire output of British Merlin production, eventually manufacturing over 55,000 engines by the war's end. Now consider what Germany would have needed to do to replicate this achievement, because German intelligence services understood very well what they were facing, and the engineers at Daimler-Benz and Junkers, who were tasked with responding to the Merlin challenge, understood it even more precisely. Captured Merlins were available, Allied aircraft fell on German soil throughout the war, and by 1942, German technical teams had accumulated enough examples to conduct thorough disassembly and analysis. What those analyses revealed was not a mystery engine whose secrets were hidden by novel patents or classified processes. The Merlin's design was, in broad strokes, comprehensible to any competent aeronautical engineer. Its cylinder configuration, its valve gear layout, its supercharger principle, none of these were conceptually beyond German engineering. What was beyond Germany's reach was something far more fundamental and far more difficult to acquire quickly. The accumulated manufacturing knowledge embedded in Rolls-Royce's production lines and supplier network, and the industrial scale to translate that knowledge into mass-produced engines of consistent quality. The metallurgical requirements of the Merlin were particularly daunting. The engine's aluminum cylinder block and head alloys had been developed through years of collaboration between Rolls-Royce and British aluminum producers, specifically High Duty Alloys Limited, which had developed proprietary casting and heat treatment processes to produce components that were simultaneously light enough for aircraft use and strong enough to withstand the stresses of sustained high-power operation. German aluminum alloys were technically excellent. Germany had been a world leader in aluminum metallurgy since the early 20th century, but they were optimized for German engine designs and German manufacturing processes, and simply substituting them for the British alloys in a Merlin copy would not produce equivalent results without extensive development work to characterize the differences and adjust manufacturing parameters accordingly. The supercharger was perhaps the single most technically demanding component, and it illustrated perfectly why reverse engineering the Merlin was not the same as being able to manufacture it. A two-stage, two-speed supercharger of the type fitted to the high-altitude Merlin variants, the Merlin 61 series that powered the Spitfire 9, and the Merlin 66 that powered the Spitfire 14, and the V1657 that powered the P-51D, consisted of two centrifugal compressor stages in series, each driven through a gear train from the engine crankshaft, with an intercooler between the stages to reduce the temperature of the compressed air before it entered the second stage. The impellers of these compressors spun at speeds exceeding 20,000 revolutions per minute, and their vanes were profiled to aerodynamic curves that had been developed through thousands of hours of testing in Rolls-Royce's supercharger test rigs. The clearance between the impeller tips and the supercharger housing was measured in hundredths of a millimeter, tight enough that thermal expansion during engine warm-up had to be accounted for in the housing design, yet not so tight that contact occurred during transient conditions. German supercharger engineering was not primitive. The DB605 and DB603 engines fitted to late-war BF109s and BF110s had single-stage superchargers of genuine competence, and Daimler-Benz engineers understood supercharger aerodynamics well. But there was a crucial gap between understanding the principles of a two-stage supercharger and being able to manufacture one in production quantities at the tolerance levels the design demanded, because those tolerances were not simply a matter of better machining equipment. They required purpose-built machine tools, specialized grinding fixtures, and an inspection methodology that took years to develop and validate. Rolls-Royce had spent that time. Germany had not. There was also the question of industrial ecosystem. The Merlin did not exist in isolation. It was the product of an entire supply chain of specialized subcontractors who made its bearings, its valves, its seals, its fuel system components, its ignition system, and hundreds of other parts, each to specifications that had been refined through years of production experience and supplier collaboration. When a particular bearing alloy caused premature wear in service, the solution was not simply to specify a better alloy. It required finding or developing a supplier who could produce that alloy consistently, testing it in production engines, accumulating enough service experience to validate the change, and then implementing it across the supply base in a coordinated way that did not create inventory chaos or assembly line disruption. This process, replicated across every significant component of the engine, represented an accumulation of institutional knowledge that could not be shortcut or reverse engineered from hardware samples, because it existed in engineering notebooks and supplier relationships and the tacit knowledge of workers who had made the same parts for years. Even if Germany had possessed all of this knowledge, the metallurgy, the supercharger aerodynamics, the machining tolerances, the supplier network, it would still have faced an obstacle that dwarfed all the technical challenges combined, the destruction of its industrial capacity by Allied bombing. By 1943, the American 8th Air Force and the Royal Air Force's Bomber Command had made the targeting of German aero engine production a priority, and the results, while not immediately decisive, were progressively crippling. The Daimler-Benz plant at Genshagen, south of Berlin, which produced the DB605 engine for the Bf-109 and the DB603 for the Bf-110, and later the He-219, was struck repeatedly from 1943 onward. The Junkers Motorenwerke facility at Dessau suffered similar attentions. German industrial planners responded with dispersal, moving engine production to smaller facilities scattered across the Reich, hidden in forests, tucked into tunnels, relocated to satellite plants in occupied territories where Allied bombers could not yet reach consistently. This dispersal bought time and maintained some production, but it came at a devastating cost to the manufacturing efficiency and quality control that precision engine production demanded. A supercharger housing that could be machined to specification in a purpose-built facility with controlled temperature, proper fixturing, and experienced workers could not necessarily be reproduced to the same standard in a commandeered furniture factory in Silesia, staffed by forced laborers who had never seen an aircraft engine component before. The forced labor dimension of this story deserves direct acknowledgement because it was not a peripheral detail but a fundamental aspect of German wartime production strategy, and it had direct technical consequences. By 1944, the majority of German war production relied substantially on forced laborers, prisoners of war, concentration camp inmates, and civilian workers conscripted from occupied territories working under conditions that were, in many cases, deliberately brutal. These workers had every reason to produce defective components and no reason to maintain the quality standards that precision aero engine production required. Sabotage in German aero engine plants was documented by Allied intelligence and confirmed after the war by survivor testimony. Even without deliberate sabotage, the combination of malnourished workers operating unfamiliar equipment under threat of violence in poorly equipped facilities produced a predictable result: quality control deterioration that showed up in engines that failed prematurely in service, in aircraft that could not maintain their rated performance, and in maintenance demands that consumed the Luftwaffe's dwindling reserve of skilled technicians. While all this was happening on the German side, the Merlin kept improving. This is perhaps the most underappreciated aspect of the entire story. The Merlin was not a static target that Germany was failing to hit. It was a moving target that was accelerating. The Merlin 61, introduced in 1942, produced 1,565 horsepower at altitude, using a new two-stage supercharger that transformed the Spitfire's high-altitude performance. The Merlin 66, optimized for low and medium altitude operations, produced peak power at different altitudes, while the Merlin 70 was tuned for very high altitude work. The V-1657, fitted to the definitive P-51D, produced 1,490 horsepower at 10,000 feet, using 150-octane fuel underwater injection, giving the Mustang a combat emergency power setting that pushed speeds approaching 450 miles per hour at altitude. Each of these improvements required engineering development, manufacturing refinement, and supplier coordination that represented hundreds of thousands of man-hours of accumulated work, and each one widened the gap between what the Merlin could do and what German engines could respond with in comparable time frames. The German response to the Merlin Mustang combination was not passive. Daimler-Benz engineers developed the DB605D with improved supercharging and higher boost pressures, and the DB603G was a genuinely powerful engine producing over 1,800 horsepower in some configurations. The Junkers Jumo 213 was a technically impressive high-performance engine that approached the Merlin in output under optimal conditions. But none of these could be produced in the numbers needed, at the quality levels required, in the time frame that mattered, and by the time any of them were available in meaningful quantities. The strategic situation had deteriorated to the point where manufacturing capacity and pilot training quality had become the binding constraints, not engine design. The Bf-109K4 of late 1944, powered by the DB605 ASCM DCM, was a formidable aircraft by any objective measure, faster than some Mustang variants at certain altitudes, highly maneuverable in skilled hands, and carrying armament that could destroy a bomber with a single burst. But there were never enough of them. Their pilots were increasingly inexperienced. Their fuel was increasingly adulterated by synthetic production shortfalls, and the men flying them faced Mustang pilots who were better rested, better trained, better supplied, and whose aircraft had been built by Packard assembly line workers in Detroit, operating under conditions that bore no resemblance to the desperate improvisation of late-war German production. General Major Adolf Galland, one of the Luftwaffe's most decorated and analytically minded fighter leaders, understood this dynamic clearly by 1944 and said so in reports to the Air Ministry that were not well received. Galland was not a man given to defeatism. He had flown combat missions in Spain, Poland, France, and Britain, and he retained his belief in the capabilities of German fighter pilots until the end. But he recognized that the equation had shifted irrevocably, that the Luftwaffe was facing an industrial monster that could not be matched by engineering talent alone, and that the Merlin engine in the nose of the P-51 represented something German industry simply could not replicate under wartime conditions. His recommendation to concentrate the remaining Bf-262 jet fighters in a single decisive engagement rather than distributing them across multiple missions was overruled, and the jets, for all their revolutionary technology, arrived too late and in too few numbers to change outcomes that had already been determined on factory floors in Derby and Detroit. The ultimate measure of the Merlin's impact on the air war is found not in a single dramatic engagement, but in the cumulative statistics of the combined bomber offensive from January 1944 onward. In the first 3 months of 1944, before Mustang escort coverage reached its full extent, 8th Air Force bomber groups flying deep penetration missions without effective fighter protection suffered loss rates that were, by any calculation, unsustainable. Missions to Schweinfurt, Regensburg, and other targets well beyond fighter range had demonstrated in October 1943 that unescorted daylight strategic bombing was too costly to maintain. The arrival of Mustang groups in sufficient numbers to escort bombers all the way to Berlin and back, a capability that existed only because the Merlin had been successfully transplanted into an American airframe and mass-produced by an American manufacturer, transformed those loss rates within months. Luftwaffe fighter strength, pilot experience, and strategic coherence declined in parallel. Locked in a feedback loop from which there was no escape, every experienced German pilot lost defending the Reich, reduced the quality of future German air defenses, and the attrition was ultimately not replaceable because the industrial and training systems that might have replaced it were themselves under attack by the bombers the Mustangs were protecting. What this story ultimately reveals is something more profound than a tale of engineering competition or industrial capacity, though it is certainly both of those things. It reveals the nature of technological advantage in industrial warfare, that such advantages are rarely located in single inventions or discoveries, but in the accumulated systems that produce, refine, and sustain them, systems built over years and embedded in organizations, supply chains, and human expertise that cannot be quickly replicated no matter how pressing the need. The Merlin was not a secret that Germany failed to sell. It was a product that Germany failed to build, and the reason it failed was not lack of engineering talent, which was abundant in Germany, but lack of the industrial depth, the supply chain maturity, the time, and ultimately the freedom from destruction that turning engineering knowledge into mass production required. Rolls-Royce had spent a decade building that ecosystem. Packard had spent 2 years adapting it to American production. Germany had neither the time nor the conditions to create an equivalent, and by the time the true nature of that gap became fully apparent, it was already too late to close it. The P-51 Mustang, the aircraft that American general officer Henry Hap Arnold called the most important warplane in American history, flew on Merlin power across Germany's skies in 1944 and 1945, and every sortie it flew was a demonstration that the industrial question had already been answered not in the design offices of Derby or the airfields of East Anglia, but in the grinding, relentless calculus of what it takes to turn an exceptional engine into a war-winning advantage and what it costs when your enemy cannot follow you there.